right? So that's something we need to identify. We are given 4 things, right? 1, 2, 3, and 4. And we know all these equations, so we can put them together and get the answer, right? This is pretty straightforward. So that's how you solve this one. It should be a good type of problem to try to practice, because when you see stuff in this chapter, it's not gonna be much more different than stuff like this. Okay. Now let's try to move on for the interest of time. So there is something else that is that propagates along the x direction, while the string propagates along the string oscillates along the y direction. Right? Each point in the string just goes up and down in the y direction. Well, and what is the equation for y? Then it is this guy, right? Now, if you want to know the velocity or the acceleration of each element in the string, we just take the time derivative of this guy once or twice, depending on what we want, right? We take the derivative of the position, we get the velocity. We do it again to the velocity, we get the acceleration. Well, this is just directly taking the time derivative of that, keeping x constant, then we get these results, right? Sine becomes cosine, cosine becomes negative of sine with some constant in front, right? So that's, yeah, so we know that this equation we have seen in the past, right? A few slides ago, and the rest is just directly taking the time derivative. So that's even a good exercise to do it at home. Now, for the wave on a string, you can actually determine the speed of propagation, which is v, like up there. We can determine the speed based on the characteristic of the string itself. So, in particular, it will be depending on 2 parameters. One is the tension within the string, and the other one is the linear mass density of the string. Now, to derive that relation, we need to look at, say, a small element of the string. Let's say the one on the peak, just for simplicity. Then we know that the peak is moving with the propagation speed v of the wave, right? Which I shall emphasize that it is different from this vy of the element. It is v, the propagation speed, not the string speed. Now, but we can try to work in the frame of reference where we are moving with the wave, and it is the string element that is moving backward. When we work in that frame, essentially what we see is that this string element is making a circular motion around a reference point O, which is of a distance r away below the P, essentially. And as a result, it is making an angle theta, which corresponds to the half length of the string element, but it also corresponds to the angle between between each end of the string and the horizontal direction, like the diagram shows. Now, the length of this string element here, it is simply twice the radius r times the angle theta, right? Because this is r theta, this is r theta. In total, it's 2r theta, delta s, the length. Now, because the length is delta s, the linear mass density mu of the string would give us the total mass of the element, which is 2 mu r theta, mu times delta s. And with that, we know the mass of the element, and then we can also determine the net force acting on the element itself. That net force comes from the 2 tensions at each end, right? Because it is pulled by the remainder of the string on each side, right? And because the tensions on each side are equal, then they're equal but not opposite, right? Their horizontal components cancel, but their vertical components add to each other. And the vertical component of this guy is t sine theta pointing down, and for this guy is t sine theta pointing down. So in total, we have the sum of the force in the y direction being 2t sine theta. And also, because the angle theta is small, we can make the approximation that sine of theta is just theta in radians. So this is a net force acting on this little string element, and it also acts as the centripetal force. If you remember from the circular motion, we see that because this string element is doing a circular motion around point O, it has a centripetal acceleration that corresponds to the centripetal force of mv squared divided by r, right? Where m is the mass of the string element, and v is just the propagation speed of the wave, right? And then that whole mv squared divided by r is that radius here to the point O. It is just the result of the sum of the tension, right? Which is 2t theta. You put the two terms together, then you plug in the expression for the mass m here, then you get this equation which we see that 2 theta cancel. So that means it gives us the propagation speed v being the square root of the ratio t over mu, t being the tension and mu being the linear mass density within the string, right? So that means the propagation speed of the wave in the string is totally fixed by the physical characteristic inside the string itself. So that is something common among mechanical waves like this. So when it comes to like something less mechanical, like the electromagnetic wave, then there is more mechanism that is going on inside, and you will see that in the second half of the course. But for the spring or when we vibrate the spring, like at the beginning, or when we even look at the sound wave, we can relate the propagation speed v to the mechanical characteristics of the medium, right? And in this case, the medium, which is the propagator of the wave, is just the string. Now, with this relation, we can try to quickly do a problem, right? So here, we consider a uniform spring, right, like this, and it is fully stretched because it is connected via a pulley to a mass of 2 kilograms. And this mass is pulling the string down, right? So it's completely stretched with some tension T. And now, if we try to generate some pulse in the string, right? The question is, say if we make a pulse here near the pulley, right, and then we let the pulse travel, how fast would the pulse be traveling? So that, and by the way, the string overall, it has a mass of 300 grams and the length of 6 meters. So that should directly give you the linear mass density. So let's see if we can find the speed of the pulse. Maybe this one, I give you like 2 minutes and then I'll do it quickly on the board. is just mu equals m divided by L, which is 0.300 divided by 6, right? So that's 0.0500 kilograms per meter, right? And then we know that the system looks something like this, right? Okay, capital M, 2 kilograms. Now, we know that in this setting, we want to find the tension within the string, right? And that is kind of like, you probably have seen similar problem in the first half, maybe even more complicated. Basically, you have the gravity mg acting on this mass, right? And so it is pulling on the string such that in order for the mass to be hanging at this point without falling, the string must exert the equal and opposite tension to mg, right? So the tension T here must be equal to mg, and it is just 2 kilograms times it is just 2 kilograms times the value of g, right? 9.81 meters per second squared, right? Then, and this is something like 18.6, 19.6. Anyway, 19.6 newtons, right? And then you want to find the propagation speed. Well, basically it is just v being square root t divided by mu, and that is 19.6 newtons divided by 0.05 kilograms per meter, right? Well, dividing by 0.05 is like multiplying by 20. You have 19.6 times 20, taking a square root is almost the average of the two, so you get 19.8 meter per second. Right. Yeah. So you just, so this is quite a direct calculation, right? The only kind of indirect thing is that you need to properly determine the tension, and in this setup it is quite straightforward because the only thing the tension of the string has to do is to balance out the weight of the mass, right? So that is okay. So that's just the propagation speed, and then so we see here that if we set up the string like this and then we just pick it up and we vibrate it, then the propagation, the pulse will be traveling with this speed. It is fixed by the characteristic, which is pretty nice. Now we can, so now we know how to determine